Good morning. VIT Bhopal University is celebrating National Science Week during 25th of February to 3rd March 2022 to commemorate the discovery of Raman effect by Sir C.V. Raman. And it is Science Day today on 28th of February. So on behalf of VIT Bhopal, our best wishes on the National Science Day to you all. This event is catalyzed and supported by National Council of Science and Technology Communications, NCSTC DST New Delhi, and Madhya Pradesh Council of Science and Technology, Bhopal. On behalf of VIT Bhopal, I welcome you all to the third lecture of the planned lecture series, which is to be delivered by Dr. Manjusha Shelke. She is Principal Scientist at National Chemical Laboratory, and she will be speaking on Ultra Capacitors, the high power flexible energy storage devices. Myself, Dr. Sharad Tripathi, and I have Dr. Pradeep Kashyap with me. We are your host for today's interaction with our esteemed guest. Dr. Manjusha has joined us. We are quite privileged and delighted to host you, ma'am, on this platform of VIT University. Welcome you. So we will have the lecture first, and then we will open the session for Q&A. You can post your queries in the chat box, which can be asked after the talk. So now I'd like to request my fellow colleague, Dr. Pradeep Kumar Kashyap, to introduce our speaker to the audience.
Thank you, sir. Dr. Manjusha Shelke is a principal scientist at CSR National Chemical Laboratory, Pune in India. She is a material chemist and her research interests are in the development of high energy electrode material for storage devices like rechargeable batteries, lithium ion, lithium sulfur, and sodium ion, and super capacitor. Her group is extensively working on energy storage solution for e-mobility as well as stationary applications and published more than 60 high impact journal publications in the area with 6 patents granted and 8 invention disclosure field. 11 of her students graduated with PhD in the area of material for energy storage. Dr. Manjusha has completed her PhD in chemistry in year 2006 from CSR Advanced Material and Process Research Institute, Bhopal, MP, India. She had worked as postdoctoral research at IEMN, France during 2007-8. Sponsored by Embassy of France in India, she had been awarded a visiting scholar in chemical sciences for the year 2013 by Indo-US Science and Technology Forum, and worked at Rice University, Houston, Texas, USA during 2013-14. She has been elected as Kavali Fellow by National Academy of Sciences, USA in 2015, and as a Fellow of Maharashtra Academy of Sciences in 2018. In 2021, Science and Engineering Research Board of Government of India awarded her with SERB Power Fellowship Institute to recognize and reward outstanding women researchers and innovators working in the Indian academic institutes and R&D laboratories. She is the founder of CSR NSL spin-off company Rechargent Energy Private Limited. We welcome you again, ma'am. It's over to you now.
Thank you very much, Dr. Kashyap. And thanks, Sharad, for inviting me to deliver a talk today for VIT Science Day function. I am really glad to come here and brief you a little bit about the research work that is going on in my lab. So, yeah, well, so shall I share my presentation?
Yes, ma'am.
So I guess it is visible, right?
Yeah, it is visible.
Yeah, well, so good morning all. As Dr. Kashyap has mentioned that I am a materials chemist and I do work on electrode materials for energy storage systems like rechargeable batteries and ultra capacitors. Currently with the boom in electric mobility, everybody is interested in batteries and the energy storage systems that are required for I'm really sorry. Yeah, and the technologies that are required for the energy electric vehicles, the energy storage systems that are required for electric vehicles. So I am also closely working with institutes like ARAI, Automotive Research Association of India, for the batteries that would be required for electric vehicles and that can make us import independent as well. So we are working on beyond lithium ion technologies as well. But yesterday only you have listened to my startup partner who also happened to be my life partner as well. And he has hacked into my talks on batteries. So I thought, okay, that will be a repetition if I talk about batteries again. So I am here to briefly tell you about another type of energy storage system, that is ultra capacitors, that is also being researched in my group. Well, so just to make a premise for the talk, I wanted to show you a little video. You know that technology and digitalization has made it easier for us to connect. And that has made me also, that has enabled me to talk to you on this online platform remotely while sitting in my home as well. So all these technological advances are based on the energy storage systems, right? So there is a lot of mobility or connectivity for which we need energy storage systems or portable energy storage system. So how these systems are digitalization as well as the energy is being a part of our day-to-day life. So just to emphasize that, I wanted to show you a small video. Yeah. To give your attention to continuing that or getting a head start. Check on
And you can increase the volume, system volume.
Sorry, yeah.
Whatever your work requires, there is always a need for synchronicity between all your platforms in the search for success. Just like finding harmony, cross-platform synchronization between all your different peers and devices allow for greater satisfaction in a world without borders or limits to your imagination. Helping you empower and secure not only your physical valuables, but securing your digital assets, whether it's on your hardware or in the cloud, as well as for your company network or personal use. Have peace of mind with our guarantee. As you unwind at the end of your day, seeking out your passions, indulging in the latest games and hobbies, in the virtual world or otherwise. Keep it all connected seamlessly. Keep life simple. Keep it smooth.
Yeah, well, so I was wearing headphones, so that was quite loud for me. Anyways, so I just wanted to emphasize that all these advances in the connectivity are powered by energy storage systems. And these are the three dominant portable energy storage systems that you are looking here: batteries, ultracapacitors, and fuel cells. Okay, so batteries, so even though I said that I am not going to talk about batteries, it is, when we talk about ultra capacitors or energy storage systems, we cannot avoid references to the batteries because that is the most mature technology for now. So there will be a lot of comparison throughout the talk, and that just to emphasize how ultra capacitors are different and complementary systems than the batteries. And then what would be the difference and how they can work together for different applications where probably batteries have lower performance and capacitors can fill up the gaps. So that is how the reference to battery will come up. Well, so batteries and ultra capacitors and fuel cells are all electrochemical systems. But in case of batteries, chemical energy is stored and then it can be converted into electrical energy. In case of ultra capacitors, the energy is stored electrostatically. And in case of fuel cell, again, a chemical energy is converted into electrical energy. So even though there is electrochemical similarities, there are certain differences in between them. The similarities are like that the a reaction or the energy is stored at the phase boundary of the electrode and electrolyte, and there will be a electron and ion separation in all the three systems. But in case of batteries, the energy conversion and storage happens in the same compartment. Like anode and cathodes are the active materials that participate in these redox reactions. So the entire energy conversion as well as storage happen within the same compartment. In case of ultracapacitors also, the energy is stored on the surface of the electrodes. But in case of fuel cells, the fuel, which is generally hydrogen or hydrocarbons, is stored in the tank. So energy is stored in the tank, but it is converted on the by the anode and cathode. So the energy is converted in the system, but it is stored outside of the system. So that is the basic difference between these three systems. And in my research group, we generally work on this system, batteries and ultracapacitors, and that is what I'll be talking about today as well. Okay. So just a minute to wipe this up. Hello, can you listen to me, Sharat? Hello?
Yeah.
Actually, my slide is not moving. I don't know why.
Okay.
Can you see now?
Yes.
Okay. So, so I was telling you that I do work on batteries and ultracapacitors in my research group. So these are the high energy density materials that we have developed in our lab for lithium ion batteries. Then we have developed materials for super capacitors as well. And we have developed the flexible ultracapacitor devices as well, which I'll be talking about today. Okay. And then my research group is also working on beyond lithium ion technologies like lithium sulfur or sodium ion batteries. And for that, I have incorporated this startup Rechargion Energy. And this is my team of my startup, the team of founders, and we have several decades of experience in energy storage system, materials for energy storage, and then experimental physics, as well as early stage academic startup management. So that's a bit about my startup, and then now I'll tell you briefly about ultracapacitors and the basics of ultracapacitors. So if you are seeing here two athletes, can you identify them? Can anybody tell me who they are? These both are these Indian athletes. So maybe you can unmute yourself and tell me. I just want to know if you can recognize any athlete beyond cricketers. Okay, so nobody knows them, right? Well, she is Dyuti Chand. Okay, she is the Indian champion of 100-meter sprint race, and she's Priyanka Goswami. Okay, and she's a champion of again an Indian athlete who is champion of 20-kilometer walk race. For Dyuti, she has to run a small distance very fast. So she has to use all her energy in a very short time to run a 100-meter sprint race. But for Priyanka, she has to walk 20 kilometer and she has to use her energy slowly for longer time, but being faster than the others in the race. Okay. So similarly, in case of ultracapacitors also, if you see here, supercapacitors have very high specific power, but they have lesser specific energy than the batteries, and batteries have very high specific energy, but the lesser specific power than the supercapacitors. So you can say that maybe Dyuti is a supercapacitor, and you can call Priyanka as a battery. So this is just I wanted to make you understand what is the role of a battery and what is the role of a supercapacitor. So supercapacitors are required where you need energy very quickly to be delivered very quickly, and batteries would require where you need large energy. So based on that, there are different applications for these systems. Even in automotives also, even though the batteries are the main energy source for electric vehicles, there are certain features in modern automotives that required ultracapacitors. So ultracapacitors have high, as I said, that they have high power performance, resiliency, and they can be used very ruggedly. So even at temperatures less than 40 degrees Celsius or higher than 60 degrees Celsius, and they can go up to several thousand cycles, even in fact lakhs of cycles without getting degraded. Okay, so certain kind of applications like this, I have mentioned start-stop technology. So this technology enables the engine in a conventional electric or hybrid electric vehicle to shut down. Okay, to shut down when it comes to a stop at a red light or while sitting in a traffic. So this system is based on an intelligent combination of engine, brake, power management, and this system that is a feature of many new high-end passenger cars. So the system stops the internal combustion engine when the vehicle is at a standstill. Okay, and as soon as the driver depresses the clutch or the brake pedal, the system automatically restarts the engine. So for this kind of application, a very quick delivery or very quick delivery of energy is required. So ultracapacitors can deliver this quick energy to support the restart of the engine during this start-stop event. And in case of regenerative energy systems, energy is captured and reused at later time. So the energy capture comes from the vehicle braking system, and it subsequently uses in the acceleration or in the support of accessory loads on the vehicle architecture. So for such kind of application also, ultracapacitors can work as auxiliary energy storage system along with batteries. And also in mild or fully hybrid vehicles, which are based on both combustion engines as well as batteries. In that kind of vehicles also, ultracapacitors are more efficient in recapturing and storing the energy, especially when it comes in bursts. Okay, so also ultracapacitors require reliable backup power solution in any event where the main power source, which is battery, is failed. For example, if there is a snowfall and the battery doesn't work below room temperature, especially lithium-ion batteries. So battery can fail if there is a snowfall. So in that case, especially for hybrid vehicles, at least to restart the batteries, ultracapacitors can be used. Okay, so these are some applications of ultracapacitors, and this is the company Maxwell that has commercialized these supercapacitors or ultracapacitors of different voltage and energy. But all of them are based on organic or liquid electrolytes, either aqueous or organic electrolytes. But today I'll be talking about the flexible ultracapacitors that are based on solid state electrolytes. Okay. So just briefly, I'll tell you the principle of the ultracapacitors. So you may know these are the conventional capacitors where two metal plates are used as electrodes, and the dielectric is or a dielectric film or oxide layer is used in between. So in this case, the capacitor, the energy is stored electrostatically as well, but they have very what you say that the energy stored is very, very less in case of conventional capacitors because they are governed by this equation C is equal to epsilon A by D. So here C is capacitance, A is electrode plate surface area, D is distance between plate, and epsilon is a permittivity of the, which is a electrolyzing capacity of a dielectric, okay, or the electric polarizability of the dielectric. So here this distance is based on the film, dielectric film, the distance between two electrodes. So that is sometime you cannot have very thick dielectric or you cannot have very thin dielectric also. So here even the electrode plate surface area is also only on the area that is on the top of the plate is considered. So in this case, capacitance is directly related to the area of the electrodes, but that is the basic difference between conventional capacitors and ultracapacitors, because in case of ultracapacitors, the electrode materials are porous carbons generally. So the metal plates are replaced by porous carbons here, and Here also the energy is stored electrostatically, but the surface area is very high. So very high surface area carbons are used, and mostly this is adsorption and desorption of electrolyte ions on electrode surface that governs the energy storage of these ultracapacitors. But in some cases, some kind of electrode materials can also undergo Faradic reactions, which are slightly different than the Faradic reactions that occur in batteries. So I'll explain that a little more elaborately during the talk. So based on this, there are different types of capacitors existing, but what Maxwell has commercialized, or mostly the commercial capacitors, are based on this double layer mechanism. And then there are recently there is a lot of progress on hybrid capacitors, where one electrode is capacitor type and another electrode is battery type. So these are called as metal ion capacitors, like lithium ion or sodium ion capacitors. So based on this, then there are three different categories of these ultra capacitors, as we call them EDLs, electric double layer capacitors, or hybrid capacitors, or pseudo capacitors. So all these differentiation has been made based on the electrode materials that are being used in these capacitors. So as I said, EDLC is mostly porous carbons or different forms of carbons, and pseudo capacitors or Faradic capacitors are based on metal oxides or conducting polymers, which can actually undergo redox reactions during charging and discharging. And hybrid capacitors, here charge storage is both electrostatically and electrochemically. So one is battery type and another is capacitor type of electrode. Okay. So just to make you understand what does it mean by EDLC and what does it mean by Faradic capacitor, I briefly want to show you some basics here. So you can see here that every electrochemical capacitor, has two electrodes. So they are mechanically separated by a separator, and there is a positive electrode and negative electrode. That is mostly all electrochemical systems are like that, even batteries or fuel cells. Okay, and but these two electrodes are connected ionically through an electrolyte. So this is the electrolyte. So this electrolyte is a mixture of, generally it is a mixture of positive and negative ions dissolved in a solvent as a water. Okay, we can replace water. So there are a lot of innovations in electrolyte as well. If we use water, then we have limitations on the voltage window. But if we go for some organic electrolytes, we can increase the voltage window, and your voltage window directly defines the energy density of the system. So that is also one of the important parameters. Well, so as I said, that every electrochemical capacitor has two electrodes mechanically separated by a separator and connected through an electrolyte. So, at each of these two electrode surfaces, there originates an area when we apply a voltage. So then this liquid electrolyte, which is in contact with this conductive surface of electrode. So this interface is forms a common boundary between two different phases of matter. Okay, this is a solid matter and this is a liquid matter. So and then when we apply a voltage, this electrochemical capacitor causes both electrode in the capacitor to generate an electric double layer. So this double layer consists of two layers of charges. One electronic layer is in surface lattice structure of the electrode, and the other, which is of the opposite polarity, is from the solvented ions in the electrolytes. Okay. So these two layers are separated by a mono layer of a solvent molecules. So if you see that when capacitor is charged, this is formed, this is the double layer is formed, and when it is discharged, the ions are randomly distributed. So this layer is called as the electric double layer. So I said that there are two layers are separated by a monolayer solvent molecules. So these are solvent molecules. So there are two layers separated, which one, this one is called as inner Helmholtz plane, and then there will be an outer Helmholtz plane also. So here it is explained very simplified way, but generally we can see that there would be an outer Helmholtz plane also. Okay, so in this process there is no transfer of charges between electrode and electrolyte. So the forces that cause the adhesion are not chemical bond. So these ions will not form any chemical bond with this solid electrode, but they are just attracted by physical forces, that is electrostatic forces. And the amount of charges in the electrodes is matched by the magnitude of counter charges in outer Helmholtz layer. So that is how the capacitor works. When it is charged, it forms a double layer, and when it discharges, the ions they just distributed randomly in the electrolyte. Okay. So the double layer phenomena that store electrical charges as a conventional capacitor. It is generally assumed that in case the way the conventional capacitors are storing energy, even in EDLC also it is same, but it is not that straightforward. Initially, it has been assumed that the same equation can be used for explaining the EDLC phenomena as well. But there was a group in Oak Ridge National Lab in USA. So they have studied these porous carbon materials, and they have come up with the hypothesis that this equation, which is used for conventional capacitor, cannot be directly applied to understand the capacitance or the energy storage system of EDLC. And that is the reason why these kind of systems give higher capacitance than the conventional capacitors. So it's not directly only related to surface area. Even the surface area is one of the important parameter here as well. So what they have suggested that the simplification of carbon electrolyte interface to an EDLC does not consider this curvature of each pore. And accordingly, the close interaction between pore walls are neglected in the simple parallel plate capacitor model. Okay, so there are different kinds of pores. You can see here. There are three types of pore exist in porous carbons: macropores, mesopores, and micropores. So macropores are generally having diameter more than 50 nanometers, and mesopores are more than 2 nanometer but less than 50 nanometer, and micropores are the pores that are of less than 2 nanometer diameter. So all these three kinds of pores have the energy storage capacity of these pores is explained with different type of mechanisms, and accordingly the equation has been modified to justify how the high specific capacitance of the ultracapacitor systems. Okay, so in case of macropores, because the pore size is above 50 nanometer, the electric double layer is a good approximation for the carbon electrolyte interface. But this equation 1 may not actually reflect the scenario for mesopores and micropores. So in case of nanoporous materials, it can have various, as I said, that even not only cylindrical, but they can have slit and spherical type, and depending on the synthesis approach. Okay, so mesoporous carbon materials obtained by templating methods usually have such kind of wormhole structures with cylindrical cross sections. Just a minute. With cylindrical cross sections, so wherein solvated counter ions enter the pores and approach the pore walls. You can see here. So these are solvated counter ions. You can see that there are solvent molecules surrounding the counter ions. So these counter ions enter in the cylinder, and they form and they arrange themselves along the wall of the pore, and they form a double layer along the wall of the pore. So this kind of capacitor, the researchers have referenced it as a double cylinder capacitor, or EDCC. So instead of EDLC, they have referenced it as a EDCC. And this double cylinder capacitance, they have given this equation 2, in which L is the length of the pores, and P and A are the radii of the outer and inner cylinders respectively. So that is how they have justified the energy storage in these mesopores. And in case of micropores, because these are so small, they are less than 2 nanometers, and even solvented counter ions have size of around 1.7 nanometers if we consider aqueous acidic electrolytes like H2SO4. So sometimes solvated and sometimes desolvated counter ions enter the pores, and they line up to form an electric wire in cylinder, okay, because probably only one counter ion can enter in such a small pores. So they form a kind of wire in cylinder capacitor. So it is called as EWCC. And the key quantity for EWCC is now no longer this D. So you can see that this is D is the distance between outer and inner circle in case of VDCC. But now here that quantity doesn't work, but rather the radius of the inner cylinder A0. So that defines, you can see here, the inner cylinder A0, that defines the energy storage in this system. Okay, and well, yeah. So as I said that by using this A0, then the energy storage inside the EWCC can be explained with this equation 3. Now, these kind of EDCC or EWCC models are based on porous carbons, are also called as endohedral capacitors, okay, where electrolyte ions can enter inside the pores. But after a couple of years, they also propose that exohedral capacitors can also exist, wherein the ions are located on the outer surface of the carbon materials. So you can see that this is the schematic of a negatively charged exohedral capacitor. It can be expected from zero-dimensional nanocarbon onion or multilayer fullerene kind of carbon materials, or one-dimensional CNTs, carbon nanotubes. So in this case, the solvented counter ions accumulate on the outer spherical surface under polarization to form an exohedral electric double sphere capacitors in case of fullerenes, or in case of such kind of spherical carbon materials. And it can form a kind of exohedral double layer capacitance in case of CNT. So we call it XEDCC. So to explain these two kind of energy storage systems, the equations were modified like this. I will not go into details of this equation, that would be too technical. But based on these assumptions, several carbon materials were evaluated over the years and used as per the specific requirement of the applications. So you can see here, the endohedral porous carbon can store higher energy, but exohedral CNTs or OLCs can be charged and discharged at very fast rates. So energy storage is more on this kind of porous carbons, but the energy delivery can be faster, more faster in case of these kind of exohedral capacitors. So based on application, then these different carbon materials are evaluated, developed and evaluated. Even in my research group also, we have synthesized these different carbon materials, right from carbon nanohorns. So nanohorns, where it's a kind of composite that we have evaluated, not synthesized, but these multi-layer fullerenes are synthesized in our lab. We have also obtained a patent for this carbon nanosheets, carbon nanotubes, porous carbon spheres. So these porous carbon spheres, even we have scaled up the synthesis. We were funded by DST for scaling up the synthesis of these porous carbons. They are not only in energy storage, they are useful in several kind of other applications, including catalysis and all. Then we have also worked on surface chemistry of these carbon nanomaterials. We have doped them with heteroatoms to add some Faraday capacitance to increase the inherent energy storage capacity of these carbon materials. Then we did try the templated porous carbon formation. So you can see that very ordered porous carbon has been formed in this case. And we did publish a lot of articles over the years. So I'll not talk about all these things. I just wanted to show you some flexible capacitor devices that we have fabricated in our lab. So this is about carbon materials I mentioned you, which are based on electrochemical double layer capacitance, and based on the different pores, we can subcategorize them into other electric double layer systems. But I told you about pseudo capacitors as well, right? So when I was explaining different type of ultra capacitors, I did mention about these Faradic or pseudo capacitors. So pseudo capacitance is generally accompanied by an electron charge transfer between electrolyte and electrode. Okay, in case of EDLC, there wouldn't be a charge transfer between electrode and electrolyte, but in case of pseudo capacitors, it does happen. So what happens, the adsorbed ion has no chemical reaction with the atoms of the electrodes, the way it happens in batteries. So there will not be chemical bond, but a charge transfer takes place. So in case of pseudo capacitance and double layer capacitance, both contribute inseparably in this case. So it's not based, so this kind of capacitor, it's not based only on a Faradic reaction, but both Faradic as well as double layer capacitance contributes to the total capacitance of this ultra capacitor. So the amount of pseudo capacitance depends not only on the surface area of the electrode material, but also on the material and its redox capabilities and the structure of the electrodes in this case. Okay. So pseudo capacitance in general, they can store a lot more energy than EDLC based capacitors. In fact, 100 times more capacitance than double layer capacitance for same surface area, just because it also undergoes a redox reaction. But the fundamental difference between redox reactions in batteries and in electrochemical capacitors is that in latter, in case of ultra capacitors, the reactions are a very fast sequence of reversible processes. So electron transfer happens without any phase change of the electron molecules. So they do not involve in making or breaking the chemical bonds, but the desolvated atoms or ions contributing the pseudo capacitance simply cling on to the atomic structure of the electrode, and the charges are distributed on surface by physical absorption processes. Okay, so in this case, if different carbon materials are used in case of EDLC, in this case, as I told you in one of earlier slides, that the materials that exhibit redox behavior are used as electrode materials. That includes metal oxides like ruthenium oxide or manganese dioxide. And they are often used as a composite with conducting carbon materials because inherently they are semiconductors. So active carbon is also used while making the electrodes. Along with them, the conducting polymers such as polyaniline or derivatives of polythiophene kind of polymers are also used as electrode material for this kind of pseudo capacitors. If you see here, these are different types of materials that are being used for pseudo capacitors. So along with traditional carbon materials, the composite of conducting polymers or the composite of metal oxides are used as pseudo capacitors, and these are the emerging new materials. You can see here black phosphorus, which is vigorously being research nowadays. Black phosphorus, which is one of the most stable, thermodynamically most stable form of the phosphorus, and it has a layer structure like graphene. So this is being used a lot. This is being evaluated a lot for energy storage systems. Then polyoxometallites, PMOs we call them. It is a family of metal oxide materials where M is in cluster form consisting transition metal oxoanions with shared oxygen atoms. So these kind of materials are also being studied. Then MOFs, metal organic frameworks. So these are a kind of compounds where metal ions or clusters coordinate with organic ligands. Okay. And then amexines. You must have heard, if you are a material scientist, you must have heard about amexines, a new class of two-dimensional inorganic compounds, the analogs of graphenes. But here they are generally transition metal carbides or nitrides kind of materials. So they are also being evaluated for pseudo capacitive pseudo capacitors or ultra capacitors based on Faraday reaction mechanism. So we have developed some such pseudo capacitive materials like polyaniline is a kind of polymer. So we have made a composite of CNT and molybdenum disulfide. Then polypyrrole coated molybdenum. One of my student has developed this porous carbon coated silicon nanowires and tested for pseudo capacitor, then carbon nanochrome and iron oxide composites. So these are just representative examples of what kind of pseudo capacitive materials we have worked on in our lab. Well, that's about the materials or the electrode materials for ultra capacitors. I'll briefly, as I said, that I'll briefly tell you how flexible ultra capacitor devices can be made. So, well, so over the years, over the past decade, with the continuous emergence of applications in various sectors, so flexible and variable microelectronic devices or systems have gained a lot of importance, right? So the commercialization of flexible electronics poses new challenge to well-established energy storage systems that are generally, even in your cell phones, the kind of batteries or systems you see, they are not flexible. Okay, they are rigid batteries. So they cannot be used for such kind of wearable devices. So you need a drastic design engineering or innovations to make these devices flexible so that they can be integrated with these emerging wearable microelectronic devices, okay, while maintaining the high quality performance under continuous mechanical deformation such as bending, then folding, twisting, and stretching, okay, while maintaining very long cycle life. Well, you know that recently the progress in implantable healthcare devices also led to new self-sustainable energy storage devices that are being developed. So that can harvest or store body energy that is generated through the actions such as breathing or arm pressing or chest compression, and it can power the smart electronics that are printed on the screen or that are that can be wearable on the screen. So the key challenge is to design and assemble flexible electrode materials with high energy and power densities and excellent long cycle life, as I mentioned. Here there is a lot of scope in innovations on electrolyte separators and flexible assembly. Even one has to consider the safety as well when you are wearing it on your body, and cost also need to be considered, okay, especially for implantable devices. So these kind of flexible solid state ultra capacitor devices are good alternatives for these kind of wearable electronics, and solid state gel electrolytes or a separator or flexible packaging material can be developed and used. And the main advantage of this flexible solid state supercapacitors over conventional capacitors is the use of solid state gel electrolyte. So, and the flexible electrodes that can be assembled in thin, light, and smart designs of any type and size or shape. Okay, so there are multiple ways to fabricate such flexible devices. Again, depending on the end application, one can choose. So these are in plane configurations. So we call them planar supercapacitors as well, where on a device some flexible substrate, the device is printed or fabricated. It is a kind of planar structure where both the electrodes are printed on the same flexible substrate in an interdigitated pattern. So then there are cable type of configurations as well. Then there are 3D sponge electrodes or 2D film electrodes, and then fiber electrodes have also been developed. And then this is a sandwich kind of configuration, the most simplest form of configuration, where two flexible electrodes are sandwiched. The gel polymer electrolyte is sandwiched between two flexible electrodes. Okay, so in my lab, we have developed flexible ultra capacitors based on the sandwich configuration and in plane configuration. So some of these examples I will show you. So this has been developed by one of my students. His entire PhD thesis was on flexible ultracapacitor development. So what he has done, he has taken this commercially available conducting carbon paper, which we generally use to test the electrode materials that we have developed. We coat it on this conducting carbon paper and make an open cell to test these electrodes. So instead of doing that, what he has done, he has taken this conducting carbon paper and then mechanically pressed it through a hot rolling machine at room temperature. So in this process, this conducting carbon paper, which is composed of carbon fibers, it loses its brittleness and becomes flexible. And then he coated it with a fine mixture of PDMS. PDMS is a kind of elastomer, polydimethylsilicone. So he mixed it with acetylene black to add, because PDMS is not conducting. So he added acetylene black to make it conducting, and he coated it on one of the one side of this flexible carbon paper to hold it, because if we roll press this carbon paper, it becomes it becomes difficult to hold it. It can break apart also. So he coated this elastomer on one side to give it flexibility as well as sturdity. Okay, and then it was dried and cured, and then a polymer gel electrolyte, which is comprising of polyvinyl alcohol along with 1 molar H2SO4 has been prepared, and then it was coated on the other side. And then he coated the active electrode material. So here he used a composite of carbon nano-onions, or the multi-layer fullerenes, and ruthenium oxide. And then two such electrodes are brought together where there would be a gel electrolyte has been sandwiched in between them. And then he made such a device. So this is the conducting carbon paper. You can see that it is made up of the small fibers. And then using PDMS, he has made it flexible. This is his active material, which is ruthenium oxide and carbon nano-onions. And this is the final device that has been prepared. So it has been tested in different conditions, like flat state or bend test, and again flattened for nearly 4,000 cycles. And there would be the capacity has been again regained when you see that it has been brought to the flat state. So we did publish it in a good journal, and we have obtained a patent also for this device. So in the next slide, I'll just show you a small video on how this has been prepared. So there is no sound for this. Okay. Yeah, well, so I showed you how he has prepared this flexible electrode and then fabricated a device out of that. And in another work, the same student has prepared another flexible device. So here, what he has done, a highly conducting flexible graphite substrate he has prepared. So how he prepared it? So we have used electrochemical exfoliation for that. So in that case, what has been done that again here a PDMS base has been used, polydimethyl siloxane, and graphene or the graphite flakes have been coated on this PDMS substrate, and then this PDMS substrate has been electrochemically exfoliated because PDMS is non-conducting, so only graphite get exfoliated into such kind of graphene oxide sheets. Here you can see, so we call them that the flexible graphite substrate. So each order, so in this case, this is direct transformation of graphite to a few layer graphene, because we are not making it into graphite oxide and then usually the way we make graphene by Hammer's method, first we synthesize GO and then we release. So here graphite has been directly electrochemically exfoliated into graphene sheets like this. So each order 2D graphene layer is interconnected to the bulk of the substrate. So that also facilitate maximum electronic conductivity. And then he has coated them with ruthenium oxide particles, nanoparticles, using sol gel technique. And on that assembly, he coated this polymer molecule. This is polyhydroquinone. Okay, so he electropolymerized again this using a monomer of hydroquinone. He electropolymerized this polyhydroquinone. So this has been used again as a redox entity, as well as it improves the surface wettability of this graphene. So this entire assembly has been again, so one electrode has been made with these graphene sheets coated with ruthenium oxide and polymer, and then another electrode, and then again a PVA H2SO4 polymer gel electrolyte has been sandwiched in between these two electrodes. And this has been also tested for nearly 10,000 cycles in flat bend fold conditions, and you can see that the capacity has been regained when it has been brought to its original position again. So this also we have published in 2019, and then filed a patent for this device as well. So same this flexible exfoliated graphene substrate he has used for coating another polymer system. Here you can see, here he has, instead of polyhydroquinone, he has used poly N-phenyl glycine, call it PNPG, which is again a pseudo capacitive conjugative conducting polymer. So it was also synthesized by electrooxidative polymerization method. N-phenyl glycine is used as a monomer here, and that has been electrodeposited on these graphene sheets that are anchored to the PDMS substrate. So same way the device has been fabricated again with polymer gel electrolyte sandwich in between two electrodes and tested. So this is also published in ACS Sustainable Chemistry in 2020. And then I was talking about, so these are kind of sandwich based devices, and this is the planar device that another student has fabricated during his thesis work. So here, instead of redox molecules like ReO2 or polymer, he has used BCN, boron carbon nitride. Okay. So boron carbon nitride is basically here he has doped boron and nitrogen in carbon matrix. So this boron carbon nitride is coated on a flexible this kind of ITO coated substrate, and then it was so here we have used a laser to make such kind of interdigitated electrodes here. We call them planar microsuper capacitor. So planar devices with interdigited electrodes are more desirable, for integration in microelectronic devices, as they also mostly having planar geometry, the microelectronic devices. The fabrication protocol for such devices usually need to be very high throughput and compatible with microelectronic fabrication processes. So generally, these MEMS are fabricated using photolithography and wet etching techniques. So here, for fabrication of planar supercapacitors also, these techniques are used, but they are extremely costly. So in comparison, laser direct writing technology is just single step process. It is very faster and suitable to write materials on flexible substrate, providing very simplified means to fabricate such devices. So as I said here, this is an electrode slurry has been coated on a ITO PET substrate, and then it was etched by using a CO2 laser. So this kind of different designs also we have evaluated. So these designs, you can, there is a program and you can make these designs in the program and give it to the system, then laser etch out selectively as per your design the electrode. So, and then you can put the solid gel electrolyte on the top of this substrate and paste. So this can be connected, one electrode can be connected to anode as anode, and another for, so positive and negative terminals can be connected here. So this device has also been tested for more than 80,000 cycles, you can see here, and it is quite stable device. So this is also published last year only. Well, and based on all this research work carried out, as I told you, one of my students' thesis was on these flexible devices. So he has constructed this prototype flexible supercapacitor device, which is incorporated into a short collar. So he made this device here, and it is placed inside a, just to demonstrate, it is a crude demonstration, but just to demonstrate that such kind of variable energy storage systems are possible out of this research. So this represents a flexible supercapacitor. It consists of 6 individual flexible capacitors that are connected in a series configuration. So a battery is also included here, and initially this capacitor is charged with a battery for a few seconds, and then you can see here that it can, there is this light, LED light has been attached, and that can be by using this supercapacitor, this we can show that the LED can be this LED can be powered by the flexible electrocapacitor devices. Well, this is a, as I said, this is a crude demonstration of the technology that has been developed, but he has got a prize from Vijay Chemicals for this innovation in one of the events. Yeah, well, so that's all I wanted to talk about flexible ultracapacitors today. And this is my lab. So we do have facilities right from synthesis of materials to fabrication of coin cells, devices, pouch cells, and testing them in several multi-channel cyclers like this you can see here. And recently we have established this pouch cell fabrication facility as well. We have BET surface area analyzer also, which is, as I mentioned, that one of the important parameter of electrode materials that defines the specific capacitance. And this is my team that has been working on all these interesting topics. Yeah, that's all. Thank you.
Thank you so much, ma'am, for such a nice and detailed description of both the science as well as the technology part of the ultra capacitors and their application to the wearable devices. So now we are going to open for the discussion. So I request my fellow colleague, Dr. Pradeep Kashyap, to take a few questions to start this discussion.
So the first question that we have is what is the difference between ultra capacitor and super capacitor? Are they same or different?
Yeah, they are same. It's just a different nomenclature. Both supercapacitor and ultra capacitor are used for same type of devices. It's just the some people prefer to call it ultra, some people prefer to call it super. That's it.
Okay. One student has asked, are the ultra capacitor already started in making in industry level, or it is just in the laboratory setups?
So solid state ultracapacitors are just in the laboratory level, but the ultracapacitors I showed you, there is a company called Maxwell that has already commercialized the ultracapacitor. Both those are having structure similar to batteries, so it's kind of cylindrical ultracapacitors with liquid electrolytes in that. So those are commercially available and even being used in several technologies as well. So if you see, there are cars with a switch. Now we can start our car with a switch, right? So in such switches for starting or stopping the car, ultracapacitors are used.
Just a last question. One student has asked what is the difference between this pseudo capacitor and a capacitor?
Pseudo capacitor and capacitor. Yeah, so I think I explained that in the starting itself. So in case of, as I showed you the schematic, the capacitors, which are normal capacitors, which stores the capacity in microfarads and generally used in rectifiers and all. So those are just parallel plate capacitors, okay? And then there are electrochemical double layer capacitors to what we call super capacitors or ultra capacitors. So in that case, porous carbons or carbon materials are used as electrode materials, and because they have very high surface area, so typically the capacitance, specific capacitance is of the level of farad. So from microfarads to farads, the increment is there in storage capacity in case of EDLC or ultra capacitors. And in case of pseudo capacitors, you can even store 10 times higher energy, because instead of only carbon materials, you can mix a composite of carbon as well as some redox molecules like metal oxides or conducting polymers. So the capacitance storage is based on combination of two principles, EDLC plus redox reaction. So typically the energy stored is very high than the pseudo capacitor, than the EDLC based ultra capacitors. So this is the basic difference between pseudo capacitor and ultra capacitors.
Thank you so much, ma'am, for giving for sparing some time and joining us in the celebration of National Science Week at VIT Bhopal University. On behalf of VIT Bhopal administration and management, I again thank you for giving your time. So there is one announcement for the audience that tomorrow we'll be having 3 lectures. One by Dr. Vasant G. Sathe. He is Center Director of UGC DA Consortium for Scientific Research in Indore. He will be speaking on the discovery of Raman effect. The next is at 10 a.m. And next speaker, Dr. Prakash Priwadgaonkar. He is emeritus scientist from National Chemical Laboratory, and he will be speaking on chemistry for sustainable development at 12:30 p.m. by tomorrow. And the last speaker for tomorrow will be having Dr. Helen Elizabeth Mason. She is emeritus reader from Department of Applied Mathematics and Theoretical Physics, University of Cambridge. She will be speaking on solar spectroscopy and ultraviolet and X-rays at 2:30 p.m. So you can tune us and you can join us for the discussion. Once again, I thank you, ma'am, for joining us. Thank you so much. Have a nice day.
Thank you very much. Thanks for inviting me. Bye.